Okay, let's go ahead and do this conversion here. So there are several conversions on this particular problem that I would not expect you to know. A couple that I would expect you to know, but the ones I don't expect you to know are basically all deal with the English system. So I think the only time I wouldn't give you a conversion factor is if I thought you really, really should know it, like how many inches are in a foot. That's probably not going to be written at the back of the test. And how many seconds are in a minute, probably not going to be written on the back of the test. But how many pounds are in a ton, if you needed that information, that would definitely be written at the back of the test. And I didn't give you any of that this time for this homework because, you could have just Googled it in 2 seconds and figured out what it was. So don't think that the lack of helpful information is what you'll see on the test. The only units I need you to know are what? The metric units. I need you to know what kilo means. I need you to know what nano means. I need you to know what micro means. But that's it. So none of the English stuff. So I'll go ahead and start off with 2.34 tons per yard cubed. What kind of unit is this? It's a bunch of stuff divided by a volume. Yeah, this is a density. So this would be a density for something like concrete, maybe dirt. Yeah, large things, cubic yard, right? We're talking about something that's 3 feet long, 3 feet tall, and 3 feet wide. So pretty big piece of dirt or substance, whatever it is. So I'll get rid of the tons first. I'll put 1 ton down here. Why am I putting the ton in the denominator? So I can't, because I don't want it, so I want to get rid of it. So I'm going to put it where it'll do the most good, which will be on the bottom. And I'll cancel that out. And then I want to get rid of this pounds. And so there are 2.2 pounds in a kilogram-ish. Good enough for this. That cancels. And then I need grams, so I'm going to go with 1 kilogram. And how many grams? 1,000 grams. Okay, so I have my mass unit. I need to convert my volume unit now. So we can do this a couple of ways. So I need to cancel out the yard unit, right? So I'm going to put a yard unit up there. I need to end up going from yards to centimeters. So I'm going to have to go through that inches thing, that 2.54 centimeters equals an inch, so I can get over to the metric system without worrying about sig figs. So if I'm in yards and I need to get to centimeters, what would I go to next? What could I go to? Feet? Yeah, sure. I can go to feet. So 3 feet and then 1 yard. Okay, so why did I put that yard unit in the numerator? So if I cancel this yard unit out, what happens to the denominator? It uses 1 of the 3 yard units that are down there, right? What does yard cubed mean? Yeah. And I only have 1 yard in the numerator right now. So I have a couple of options. I could do this right here 2 more times. Because then that would put 2 more yards in the numerator and 3 feet on the bottom. Not 3 feet, but a foot times a foot times a foot. And I need to make sure that bottom unit is what unit? Volume unit, right? So it has to be a length times a length times a length. So if I only did this once, I'd still have 2 yard units on the bottom and I'd only have 1 foot unit. So that's not going to work out for me. Okay, so I could either do this 3 times or I can say cubic yards. But if I do that, every single thing, number and unit, I have to do the same thing to it. So cube the 1, which obviously doesn't do anything, cube the 3, and cube the foot. Are we okay with that? Because really, what does that mean? The thing that I had there before, right? Just 3 times. I've copied it 2 more times. So now I've got my yards cubed, and they're gone. So I've got a volume unit in the denominator, and it's feet cubed. So, okay, that's That's closer to centimeters cubed than yards cubed. So how do I get rid of the feet? So I'm going to go feet here and inches here. And so what else am I going to do? 1, 12, cube, 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 cube. And now the feet cube are also gone. So now I got inches cubed. I want to get rid of that. So inches and centimeters and 2.54, 1, and then cube, 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 cube. Inches are gone. And so what I have left are grams per centimeter cubed. So I've got 2.34 times 2,000 times 1,000 divided by 2.2 divided by 3 cubed divided by 12 cubed divided by 2.54 cubed. I got 2.782 and some other stuff. But how many sig figs do I get? 3. So the answer here is 2.78 grams per centimeter cubed. Are we okay with that? That one was kind of complicated, so. But tell me what units I expect you to know in this unit conversion.
Centimeters.
That one right there, and I guess this one right here. Just common knowledge for that second one, but the first one is the only one that I would expect you to have memorized from this class, but maybe you already knew that one. But the rest of them, I would give every single one of those to you. The only units I need you to know are the really super common English ones. And how many zeros do I need to make grams equal to kilograms? That's what you need to know. No, okay. Remember that like fourth thing on what you're going to do in this class from the syllabus? What was that? I don't remember. Use math that you probably never thought you'd use. There we go. All right, so I need to do a little bit of algebra with this one. I need to get that temperature Fahrenheit out of there. So what do you want to do first?
Get rid of the fraction.
Okay, so if I take this fraction and multiply it by 9/5, the 9 cancels, the 5 cancels. We got to do the same thing on the other side. So I got a 9 and a divided by 5. All right, so that's fine. What next? Yep, if I add 32 to this side, that thing disappears, and then I can add 32 to this side. And so I'm going to end up with temperature Fahrenheit is equal to, 32 plus 9 divided by 5 times temperature Celsius. Does it matter where I put that plus 32? Why not? Because the order of operations would dictate I have to do the multiplication and division before the addition anyway, so you can put it wherever the heck you want. Is there anything that was not needed in the given equation? Which ones? This doesn't really need to be here, right? Calculator would just ignore those. It knows it's multiplication and division, and it's going to do that. Anything needed? The other parentheses is required. Without the other parentheses, tell me what would happen. It'd do 32 times 5 divided by 9, and then it would subtract that quantity from my temperature Fahrenheit, and that would give you the wrong answer. Okay, so how about this one? You got a car with over 300 horsepower, you're driving into Canada, and it says 125. Is that a yeah? No, it's not. It's kilometers, right? The problem with this situation is This is a 1966 Ford Mustang. Do you think it's got that up to 160 miles an hour and on the inside it tells you what the kilometers are? No, we really didn't care about stuff like that in 1966. So it just has the miles per hour. So you kind of have to do the math as you're driving through Canada. All right? It's about 60%. So if I multiply 1.25 times 0.6, that'd be about my number, but we'll make it be really accurate with this one. All right, so I'm going to start off with 125 kilometers per hour. If you cross over into the Canadian border, they usually say, hey, don't forget it's kilometers, especially if it's an old car. But they have Mounties in cars parked every 3 miles for like the first 30 miles. Why? Because you're going to see that 125 sign and just go to 125 and then get pulled over and pay a big ticket. Welcome to Canada. 1 kilometer, 1,000 meters. Why did I go to meters? I'm trying to get it over to miles, right? And I need to get into, so miles is feet, and then what's my conversion? Where's my pathway from this metric system over to the English system? That 2.54 centimeters equals an inch. So I got to go through that for this to be exact. So 1 meter, 100 centimeters. And then 2.54 centimeters is 1 inch. And then 12 inches is 1 foot. And then 5,280 feet is 1 mile. So I got my feet and my inches and my centimeters and my meters and my kilometers all canceling out. The units I have left are miles an hour. So I got miles per hour. And then if I do this, I get, what do we get? 125 times 1, 2, 3, 1, 2, divided by 12, divided by 2.54, divided by 5,280 equals. We get 77.6714. Is that my answer? What is it? 77.7 miles per hour. Okay. Which units would I expect you to know in this one? Conversions.
Meters.
This one? What else? This one? What else? I just kind of expect you to know that one. The other ones, they'll definitely be, if you need them, they'll definitely be given. Okay. So, it's Columbia River, it's water. What's its density? About 1 gram per milliliter. So if I've got something in that river and that thing is floating, what's that thing's density? Less than 1. So I need the density of this to be not greater than, less than 1 gram per centimeter cubed, or milliliter, whatever, doesn't matter. Okay, so if I have a mass of 45 grams and a mass of 135 grams, that gives me a mass of 180 grams. Okay, so I need to have a unit that's grams divided by centimeters cubed, and this number needs to be less than 1. So tell me about the milliliter or the centimeter cubed unit right here. Tell me about the number. It's got to be greater than 180, right? So if this is, say, 181, what's this bag and phone going to do? Float. If it's 100 what if it's 200? It's going to float higher out of the water, right? If you had this situation and your phone fell out of your pocket or slipped out of your pocket while you were in the water, what would you want your phone to do? Kind of float and stick out of the water, because it's the Columbia. You'd want to make sure that it was like sticking out of the water a little bit, or that the case was bright orange or something like that. And what if it was 180 exactly? What if its density was also 1? What would happen? If it was a bathtub and you set this thing into it, what would happen? Wherever I let go of it, it would just stay there, right? Because the bathtub's water isn't moving. But the Columbia, what's happening? So the water is moving along, and this is just there's gonna be some current circulating, right? So what's this phone and case gonna do? Circulate exactly like the water does. So and eventually at some point it's gonna bump into something and probably get stuck and be underneath the water. But it's not sinking, it's not floating, it's got the exact same density. So somewhere in the Columbia, there's like an iPhone 3S in a perfectly water-safe case. It's probably been there, it's maybe 5 years now. So if anybody finds it, it's mine. I'm sure the battery's dead. I did not. That was my problem right there. Yeah. It's very sad about that. And really, it was like totally stupid. You know, this section from the event site to the spit, it's like 20 feet wide. Do we know what I'm talking about? And sometimes it's like calf deep, and sometimes it's like waist deep. It was waist deep. By the time I got to the other side, I stood up and was like, my pocket feels light. It's gone. I mean, it was only in the water for like 4 seconds. I still couldn't find it. No idea where it went. Okay, what's really important about these two theories? Huh?
What are the initial, the starting studies?
The jumping off point?
Led to the discovery of the structure of data.
How is this a starting point though? Well, they're 100% right in the fact that they're atoms. A lot of their stuff about it was wrong, but imagine that you're trying to learn about stuff, but you have no idea what the stuff is about. So think about the people who first found Egyptian hieroglyphics. Where do you start? Like, I have no idea what this is about. What does that bird mean? What does that bird mean? What does that cat mean? What does this symbol mean? They needed a jumping off point. As soon as they got the first something or other, then you can figure it out. If you watch any movies that deal with codes, as soon as they figure out one letter, what one letter is in the code, then they can get the entire code. Once they know that, you know, every single one of these letters is an A, they can shove that into a computer and be like, this must say this, kind of thing. But getting that first one is hard. So having the point to base all of your experiments off. So right after this happens, right after Dalton comes out with his theory, and a little bit before that, a bunch of guys started doing stuff with the thought that what I'm looking at is a bunch of little things made of atoms. So this is baking soda, and so they could do an experiment on baking soda, not thinking that this is just a chunk of stuff, but this is what? A bunch of tiny little things. That completely changes the way you're looking at the experiment. If you realize what I'm looking at is a bunch of identical tiny little things instead of a chunk of something or other. So they looked at this and said, there's a bunch of things here. Instead of there's something here. There's like one thing here. There isn't one thing here. There's a bazillion little things here. And once they decided that, hey, this is working out for us, they figured out a whole bunch of things. Like almost immediately figured out water's formula was H2O. Like took zero time at all after they were thinking about atoms. Okay, so starting point, we can base I can think of an experiment and base my experiment on the fact that I'm looking at stuff made of a bunch of atoms. So you base your experimentation on the premise of the atom. How about this next one about the magnitude of the charge? They are equal to each other. Even though this thing is 1,800 times smaller than that thing, mass-wise, the plus and the minus are actually equal to each other in their size. So if I had one proton and one electron, even though the electron is 1,800 times smaller, when they come together, what's the overall charge of that thing? 0. They cancel each other out. Nothing. Dalton, what's he say happens during a chemical reaction?
Rearranges.
Combined, separated, and rearranged. Super important, because once we realize this, we could understand that all I'm doing is rearranging the matter in the universe. There isn't any magic stuff happening. There's no earth, fire, earth and water stuff happening. There's no life force of the universe causing this all to happen. This is just things that I'm disassembling and putting back together in a different order. And I mean, they didn't have Legos back then, but they could understand disassembling something and putting it back together to make something new out of it. Why is Dalton happy that water is H2O? Yeah, that is always water. What else? Whole numbers. And it's a 2 and a 1. Not like 7,222 to 43. It's very simple whole numbers.
Question, Rob.
Yo.
For the elements, is there any that's like a crazy, like you were just saying, like say 50 oxygen and like 75 something else to create something?
For the molecules, you make it out of that? Sure.
Can you do it?
Proteins. When we're talking about size of proteins and things like that, we changed the units to something called Daltons, named after this guy. And the unit is actually a lot bigger than the AMU, because the AMU number would be a really long number to write, because there are so many atoms associated with that. So are we familiar with proteins made of, or what? What are they made of? Amino acids. So sometimes the chains on those proteins are really long, and then sometimes those proteins actually do not function by themselves. They're sort of like parts to a larger piece of machinery. So great, the handlebars on my bicycle are great, but I mean, they're not a bicycle. It doesn't do anything without all the rest of the parts. So I might be taking long chains of amino acids, giving me many, many atoms, and I have to connect that to another piece that gives me even more atoms to deal with. So yeah, we can get some pretty big structures. I mean, DNA. Does anybody know how many base pairs there are? Humans? 3 billion. So I got 3 billion base pairs, and each one of those base pairs has like 12-ish plus atoms, 12 to 20 atoms. So we're talking about a lot of atoms. So yeah, we can make really, really giant stuff. But when he was talking about this, he was mostly talking about things that were inorganic stuff, not living organism stuff. How about this one about empty space? How do you defend that? Anybody who's like, I'm not empty space, I'm stuff. Yeah.
Matter made of atoms and atoms.
Okay, so stuff is matter. Matter is atoms. And the mass where's the mass in an atom? In the nucleus. Okay, so how big is the nucleus? Ish. 10 to the minus 15 meters. And the size of the atom? 10 to the minus 10th meters. So the nucleus is 100,000 times smaller than the atom, and the mass is in the nucleus. So when you're looking at this, 1 out of every 100,000 times you throw something at it, you're going to miss, because it's just a pinpoint where all the mass is crammed down into a tight, dense, positive core. But for the most part, it's just a bunch of empty stuff. You could have drawn something like atom, nucleus, and said those are my nuclei. And then this is just space. Just a bunch of empty space there. And this is, again and again, over and over again. And so not much actually there.
You can also use like static electricity, concentrated, they still have like low ion behavior. Static electricity, we all can use things with alternating
this is totally electric, and if they can't picture how the static electricity thing works, like, well, you're not upset about the fact that magnets have an invisible force field, are you? Or, I don't know, jump. Did you stay up there? There's another invisible force field, so it's an invisible force field that you deal with every single day. How about, so sulfate? SO4 minus 2. Sulfite? SO3 minus 2. Nitrate? 3 minus. So now that I know nitrate, what's nitrite? I know 2 minus. And then the ammonium? NH4 plus. It's one of the only positive ones on that list of polyatomic ions. Okay. Walter?
Question on those.
Yep.
For the first test, you said we need to have these memorized. It's the same for the periodic table.
Yeah. I mean, the only thing with the periodic table stuff, remember, is you need to know that what atoms are in that sulfate molecule? Sulfur and oxygen. How do you know that? Because S is sulfur and O is oxygen. I don't need you to know where it is on the table. I don't care that you know that the sulfur has 16 protons in it and the oxygen has a mass of 16. Those aren't important. I just need you to know that if there's an O written someplace in a formula, that you go to the table to find oxygen. Or if it says potassium on the periodic table, in a question, where do you go on the table? You look for K, not phosphorus, which is P. That's what we're looking for. When it says sodium, you're not going to go look for what letter? S, because that's sulfur. That's all I'm interested in. You don't need to know positions, just what each symbol. If the word of the element is written, you need to be able to find it on the table. That's really the point.